All right, I am not going to read you this part, but if you have not read this yet, you really should stop the video and read over that. You might highlight some things. It gives you a lot of hints on how to set up these problems. So I'm just going to start in with some examples. So we're going to cover problems 4, 5, and 6 in this video. So an oil tanker leaks oil that spreads in a circular pattern whose radius increases at the rate of 50 feet per minute. Now, even as I read the problem and I see the radius increases at the rate of 50 feet per minute, I'm going to write down dr dt equals 50 feet per minute. How fast are the circumference and area of the spill increasing? So in my mind, I'm thinking I've got to find dc dt because I want to know the rate of change. How fast is the circumference increasing? How fast is the area increasing? So I want to also know dA dt for given values of the radius. So that means I'm going to need to know the circumference formula in terms of the radius, since it's all in terms of the radius. So we know circumference is 2 pi r. And I'm also going to need the area formula, which is pi r squared. So then I need to find the derivative of this with respect to t. So I get dc dt equals 2 pi is a constant. So we get 2 pi and the derivative of the radius with respect to time. So this is what I get. So now I start plugging things in. I want to solve for dc dt when the radius is 20. Well, notice on this, there's not even a place for the radius, so it doesn't depend on the radius, it only depends on dr dt. So dc dt, which remember represents the change in the circumference, is 2 pi times 50. So I get 100 pi, and this would be feet per minute since it's circumference. And so this is my answer for dc dt. Now, Part A asks when the radius is 20 feet. Part B asks when the radius is 50 feet. dc dt is the same. The change in the circumference is the same for either of those two cases. So now I'm going to deal with the area. So I'm going to find dA dt. Using the power rule, I get 2 pi r. And then because it's implicit differentiation, I have dr dt. And that's basically the chain rule in action. So now, to solve part A, I want to know when r is 20. So I have dA dt equals 2 times pi times 20 times dr dt, which was 50. So then we end up with 2,000 pi. And we have square feet per minute. Okay, then in part B, we have r equals 50. So for dA dt, we just plug in a 50 for r instead. And dr dt was also 50. So we get 5,000 pi square feet per minute. Okay, so when you pay really close attention to things like when it talks about how fast, it's a rate. So you think about, what formulas you need. You take the derivative. This one is not too bad. All right, next problem, kind of a classic problem in calculus when you talk about related rates, the old ladder sliding down the wall. So we have a 13-foot ladder leaning against a vertical wall. So I'm going to draw a picture. So here's my 13-foot ladder. And here's my vertical wall. So I'm going to label some sides, and I'm going to call this Y since it's vertical and X for the horizontal. And it says if the lower end of the ladder is pulled away at the rate of 2 feet per second. So we're pulling, here's the base of the ladder, we're pulling it away from the wall at a rate of 2 feet per second. Well, if I call this distance x, then I'm going to call this rate of change dx dt, and that's going to be 2 feet per second. It's going to be positive because it's being pulled away from the wall. So that would be dx dt. The question is, how fast is the top of the ladder coming down the wall? Well, that's talking about a vertical change. So I'm being asked to solve for dy dt. So that's my unknown. And it says, how fast is that occurring? At the instant the top is 12 feet above the ground. So this is going to be for later. I'm going to plug it in. So this is going to be telling me y is 12. And then again for part B, y is 5. But those are not constants because y is changing. X is changing and y is changing. The only thing that's a constant is my hypotenuse of this triangle, which is a hint on how we're going to solve this. Because we have a right triangle, it should make you think Pythagorean theorem. So I'm going to write down x squared plus y squared. Since this is a constant, I can just call it 13 squared. And then I'm going to take the derivative. I mean, you can actually calculate 13 squared, it's 169, but it really doesn't matter because the derivative is going to be 0. So we're going to have 2x dx dt plus 2y dy dt equals 0. So there's my derivative. Now be careful, you can't start plugging things in until you actually find the derivative first. So I remember having a student once who would get to this part right here and then plug in like the x and y values, and then would always tell me the answer was 0 because they would take the derivative of a constant and it would be 0. So you can't plug in those values that are changing. You can't plug them in until after you take the derivative. So now we could, we know the value of y for part A is 12, but we need to know what the value of x is. And we can make use of the fact, so if y is 12, and we know that my hypotenuse is 13, so we're looking at this. So we have 12, we have 13. If you are familiar with Pythagorean triples, you might know that there's a 5, 12, 13 triangle. Otherwise, you can just solve for x. So x squared would be 13 squared minus 12 squared. And if you do that math, you'll get 25. So x is 5. So then for part A, I can plug that in. So I'm going to have 2 times 5 times dx dt, which is 2, plus 2 times y, which is 12, times dy dt, which we don't know, equals 0. And then you can solve this for dy dt. I'm just assuming that you could all do that. So we get dy dt equals negative, if you change it to a fraction, because it was a repeating decimal, negative 5.6 feet per second. So that would be part A. And then part B says, okay, well now what about, what's dy dt when y equals 5? So then the triangle now, it's going to look more like this. So now here's the 5, here's the 13, which means this has to be 12. So if y is 5, x has to be 12 in order for that to work. So we're going to have, we plug it into our equation, so we have 2 times 12 times dx dt, which is 2, plus 2 times y is 5 times dy dt, we don't know, equals 0. And if you solve that, you get dy dt equals, and if you write it as a fraction, it's negative 24 fifths. I'm not showing that, you know, because I figure you guys could all solve that for dy dt. Okay, so that takes care of that problem. Number 6, a camera is mounted. By the way, as soon as we see that we've got this triangle again, we know that we're probably going to use Pythagorean theorem here. A camera is mounted 3,000 feet from a rocket launching pad. So here's the camera, here's the rocket launching pad. So this distance here, which, you know, I'm going to label as an x, but it's mounted it's a constant. So this is 3,000, and it's a constant. Which means constants can be plugged in, excuse me, constants can be plugged in before you take the derivative. The camera needs to swivel as the rocket is launched to keep it in focus. If the rocket is rising vertically at 800 feet per second, well, I'm going to call this y, and then write down that dy dt equals 800 feet per second. When it's 4,000 feet high, well, this is a value of y, but it's changing. How fast is the camera to rocket distance changing? So the camera to rocket distance is this right here. I'm going to call that z. So we are looking to find out how fast that distance is changing. So I want to know the value of dz dt. Okay, so then I kind of get that idea of what I'm trying to find out, and I know that I have a right triangle. So I'm going to start with the Pythagorean theorem, x squared plus y squared equals z squared. So you can plug in constants before you get started, because since it's constant, we're going to have 3,000 squared plus y squared equals z squared. And now we can do the derivative with respect to t. But the derivative of a constant is 0. So then I get 2y dy dt equals 2z dz dt. And now I should be able to plug values in. So the first question says, so we're finding dz dt. So we know dy dt, so I'm going to plug in that. So we have 2 times y is 4,000. This is part A. Dy dt is 800. And do we know z? Oh, we got to do that calculation. So back up here, we know that 3,000 squared plus y squared would be 4,000 squared equals z squared. Okay, because now we're plugging in the y equals 4,000. So we want to know the value of z at the moment in time when y equals 4,000. So we're going to use those values and plug that in. And when you do that, you're going to get z equals 5,000. This is a 3, 4, 5 triangle. You can do the math if you want to, but that's what you're going to get for z. So we have 5,000 dz dt. So when we solve this, we get dz dt is, if you do the math here and solve for dz dt, you will get 640 feet per second. And you might want to verify that. I mean, I know that's the answer, but you might want to verify that you can get the answer as well. So that's part A. Part B asks, how fast is the camera's angle of elevation changing at that particular moment in time? So that means when y is 4,000. How fast is the camera's angle of elevation? So we're talking about right here, I'm going to call this theta. So as the rocket goes up, this angle is going to increase, and we're trying to find what that value is, which is d theta dt. So for part B, they actually tell us that here. For part B, we're looking for d theta dt. And we have a right triangle, which means we're going to use a trig function. And the author has, says that they're going to try all 3 and determine which is best. So I'm not going to do all 3. I'm going to just do the one that's best, and we'll talk about why it's best. So if you look at sine theta, opposite over hypotenuse, so you're going to have y over z. Cosine theta is adjacent over hypotenuse, so you're going to have x over z. And tangent theta is opposite over adjacent, so you get y over x. So notice that if you use either sine theta or cosine theta, it requires that you have figured out the answer to part A before you can do those, because it has z in it. If you look at tangent theta, this one does not require the answer from part A. And there's another really good reason for choosing this one. Look at your denominator here. X, remember x is a constant. So sine theta doesn't involve the x. It doesn't involve a constant. So it's going to be more work. This one, the x is the constant, but then this z is in the denominator. So I'm going to kind of have to use the quotient rule here. But here, since x is a constant, so the denominator is a constant, so we avoid the quotient rule. And you know I'm all about avoiding those rules if I can. So I'm going to use tangent. All right, so we decide that. As a matter of fact, I can actually plug this in and say tangent theta equals, I'm going to write it as 1 over 3,000 times y, because x is a constant, so I can actually put that in before I do anything else. So now I have to take the derivative, remember with respect to time. So the derivative of tangent is secant squared. So I get secant squared theta times d theta dt, don't forget that part. If we did, that'd be bad because it's what we have to solve for, equals 1 over 3,000 dy dt. All right? Now remember, we're solving for d theta dt. We know dy dt because dy dt is 800, so it's still from the previous part of the problem. So we have to work with this secant theta because we've got to figure that out. So I'm going to sketch a little triangle over here in this space that I'm not using. And we had, this was the constant, 3,000. Now we're ready to plug things in. So remember, it's the moment in time when the vertical distance was 4,000. And this is a 3, 4, 5 triangle. We already solved. We said that z would be 5,000 then. So at that point in time. So then if I want to find secant theta, here was theta. So secant theta, I think about cosine. Cosine theta would be 3,000 over 5,000. So secant theta is 5,000 over 3,000, or just 5/3. So then secant squared theta is just 25/9 because you just square that. So I get 25/9 times d theta dt equals 1 over 3,000. And remember, dy dt was 800. So do the math. You're going to 800 divided by 3,000 multiplied by 9/25. If you do the math there, you get d theta dt. And I use my calculator and I got 0.096. And remember, with theta, we're dealing with radians. So this would be radians per second. And that would be the rate of change of my angle, the camera angle. Okay, so that gives you some examples to do, and you have an assignment from the homework section.